Hello everyone. Today we are looking at one of the most fundamental properties of our universe, electric charge. We see its effects in lightning, depend on it in everyday technology, and it plays a key role in holding matter together. We understand how it behaves and we have learned to use it well. But if we ask a deeper question, what is charge really? The answer becomes less obvious. In this first part, we begin with the simple observations and gradually move towards some more complete, somewhat complex understandings. Let me take you through a bit of a history of electric charge and electromagnetic fields. It all begins with the Thales of Miletus, who noticed that rubbing amber could attract small objects, a simple observation that sparked centuries of curiosity. Over time, pioneers like William Gilbert and Benjamin Franklin transformed these mysterious effects into something measurable and understandable. The work of Charles Augustin de Coulomb and Carl Friedrich Gauss then gave us the mathematical laws that describes the how charges interact and how electric fields behave. Building on this, Michael Faraday introduced the idea of fields, which was later unified beautifully by James Clerk Maxwell into complete theory of electromagnetism. Finally, their experiments by J.J. Thomson and Robert Millikan showed that charge is carried by tiny particles, opening the door to a modern quantum physics. Let us begin with a precise definition of what is electric charge. Electric charge is an intrinsic property of a certain fundamental particles. By describing it as intrinsic, it means the charge is not something that can be added or removed arbitrarily. Rather, it is a fundamental characteristic of a particle itself. In the same way that particles inherently possess mass, certain particles inherently possess electric charge. One useful way to interpret electric charge is an quantitative parameter that determines the strength of the particle's interaction with electromagnetic field. In this sense, charge can be viewed as a numerical value. Particles with a zero charge, such as neutron, do not experience electromagnetic forces, whereas the particles with a large magnitude of charge interact more strongly with the field. An equally important aspect, first identified by Benjamin Franklin, is that charge exists in two distinct types, positive and negative. These are represented using the mathematical sign because they follow clear algebraic rules. Most notably, opposite charges can combine to produce a state of neutrality. This principle of balance explains why most macroscopic objects appear electrically neutral under ordinary conditions. The positive and negative charges within them are typically present in equal amounts, effectively cancelling each other's influence and preventing any noticeable electrical effects in everyday experience. To properly understand the electric charge, it is essential to first establish a clear understanding of concept of field. In mathematics, a field is an abstract structure, a set of numbers equipped with specific rules of operations such as addition and multiplication. In physics, however, the meaning is more concrete and physically significant. A field is best understood as a continuous medium that exists throughout the space and time with a well-defined value at every point. This medium is not material in conventional sense, yet it plays a fundamental role in describing physical reality. It carries information about physical quantities and governs how interaction occur. Imagine the room you are in. Every single point in this room has a temperature. This is a temperature field. In the case of electromagnetic field, each point in space is associated with the values that determine the force a charged particle would experience if placed there. A mathematical field provides the language to describe a physical field, where the physical quantities like force or energy vary over space and time. For example, electric field of charge is represented mathematically as a vector field assigning a force direction and magnitude at every point in space. This is where simple becomes complex. In the classical view, electric charge is treated as a continuous quantity. It can in principle take on any value, 1 unit, 1.5 unit or even 1.0007 units, and is often compared to fluid that flows smoothly. This approximation is widely used in introductory treatments because it simplifies both visualization and mathematical analysis. However, the modern quantum perspective reveals a more fundamental picture. Electric charge is not continuous but quantized. It exists only in discrete units. One may have the charge of a single electron or an integer multiple of it. In this framework, interactions are no longer described as purely smooth and continuous processes. Instead, they arise through an exchange of particles known as photons within an underlying quantum field. When two electrons repel one another, this can be understood as an exchange process. They effectively transfer momentum via photons, leading to observed force. The quantized nature of charge, first convincingly demonstrated by Robert Millikan, fits naturally into deeper description of electromagnetic interaction. We have traveled from simple act of rubbing amber in ancient Greece to deeper understanding of electric charge through two complementary views: the classical, where the charge appears continuous, and the quantum, where it is fundamentally discrete. But believe it or not, we only scratched the surface. The deeper questions are: why does the charge behave the way it does? Is it the property of electromagnetic field itself or of the particle that carries it? Are charge and electromagnetic field the same or they are fundamentally different? In part 2, we will dive into why questions and proceed to examine how electric charge fundamentally governs and defines the structure of physical reality. For now, stay curious, keep asking questions, and thank you for your time.